The lens maker's formula. As you know, lens is a combination of two spherical surfaces. This formula is known as lens maker's formula. Using this equation, you can design a lens with desirable characteristics. Using these lenses, we fabricate many optical instruments like microscope, telescope, camera, and eyeglasses. These lenses are fundamental components for manipulating light. The focal length of a lens, which may be a convex lens or concave lens, is the fundamental property. Focal length is the fundamental property, which implies how strongly a lens bends light to get a magnified image and its position at the expected point. That is the importance of focal length. And the focal length of a lens in an instrument, the specific function of a particular lens, it depends on its position in the instrument as well as focal length of the lens. Focal length of a desirable value should have some desirable value. What would be the value for that function? To get the desirable value of focal length of a lens, we need to calculate using the formula. It requires computation of the values using this equation. The equation, this f is a function of these refractive indices, refractive index of the lens, refractive index of the surroundings, and radius of curvatures of the two spherical surfaces. You have to calculate what would be the desirable value of focal length, for which what would be the possible values of R1, R2 and N2? What would be the possible values of R1, R2 and refractive index of the glass to get the desired value of F? That requires calculation. Accordingly, the lens is made. The lens is made always in accordance with the equation. For a possible value, that is for a desirable values of F, what would be the possible values of these? That is R1, radius of curvatures of both the spherical surface, and refractive index of the lens. This equation, how do you get this equation? By derivation. We derive this equation by the following position. I am taking this lens, convex lens. You can also take concave lens. This is the optical center, and these are the centers of the spherical surfaces. In most of the cases, we use very thin glasses. If that is the case, these points assumed to be coincided. that is a convex lens or concave lens. And this line is called as principal axis. The object and the image always lies on the principal axis. Here if you keep the object on the principal axis like this, and a ray of light is from this object supposed to be in this direction, it undergoes refraction at this spherical surface. This lens has two spherical surfaces. This is one spherical surfaces of center of curvature C1. The distance between this and this is called as R1. And this is another spherical surface, that is 2, whose center of curvature is C2. The distance between this and this is called as R2, radius of curvature of this surface. At this point, the light undergoes refraction. As you know, this is N1, this is N1, this is surrounding surface. And this is the refractive index of the glass. Refractive index of the glass. And it may be greater than N2 is greater than N1. Look at this. At this point of refraction, light undergoes what is that? Refraction like this direction. If there is no spherical surface like this, the light would have traveled along like this, data image I1 like this. So this would be the I dash. I can call this as image for this object due to this refraction. But here there is one more spherical surface come across where it undergoes one more refraction. The light would not travel like this, undergo another refraction because there is a difference in refractive indices. This is N2, this is N1. It is higher, this is lower. So what would be the refraction at this point? So at this point, for this surface, the normal, always this is a straight line passing through center of curvature and this point of refraction. And because of lower refractive indices, the light ray is bending away from this. From this side it is bending away. Instead of going like this, bending away and touches this point. It is the image formation due to this refraction. And here at this point of refraction, what would be the normal to this surface? Normal to the surface is, it is the center of curvature of this surface and this point. That is a straight line. And while during refraction, it is bending towards the normal. So going like this, bending towards the normal because going from lower refractive index to higher refractive index. So that is the direction of the ray, and direction of the ray after refraction from this point. And this is what, for this refraction, this is what is that U. I am talking about the spherical surface. In this refraction, this is U is the object distance like this, and for this refraction, this is the image distance. Image is here. Image distance I can call it as VI. VI image distance. N2 is this. This is N2 here. And this is one refraction, that is refraction at one surface. What would be the refraction at another surface? At this surface. This is one I am calling separately, written separately. The same diagram with the spherical surface like this. At this point of refraction, here the refractive index is N2, refractive index is N1. This is the direction I told you. This is the direction for the image for this refraction. This is the image due to this refraction. What would be the object for this refraction? Here coming from this like this. So object for this refraction is this one, I1. What is I1? Image due to this refraction. This image now behaves like an object for this refraction. This object is known as virtual object. So, need to understand, for the refraction at this surface, this is the object. The distance of object is, I can call this as V1 self in here, because thin lens are taken. The distances remains same almost. So this is the object distance for this refraction. Object is this, and this is an object V dash, and this is V is the image distance for this refraction. Image is here and this point, center point V. So with these all these values, there are two refractions or two spherical surfaces, and let me recall the equation for refraction at spherical surface. This is the one I have derived, and this is what I applied for this one. And we have to use our technique to apply this equation for this refraction. Apply this equation for this refraction. How do you apply? You have to apply some technique. The technique is, I am calling this as initial state, this as final state. Light is passing from here, from this state to this state. This is initial value, this is final value. Object distance, image distance, and R is the radius of curvature of this spherical surface. So this is what the equation for this refraction. Look at that. For this refraction, N2 final value minus initial value. Final value minus initial value divided by R radius of the curvature of this spherical sphere equals N2 final value divided by image distance minus of initial value divided by the object distance. This we have to remember, and the technique is very important to apply at any point of refraction. So if you do so, here apply this. Let us understand what is U, what is V. V dash. U is the object distance, V dash is the image distance. Initial value is N1, final value is N2, and radius of curvature is R1 because C1 the first one. Apply the equation. Final value minus initial value. This is final value because light from here to here. Initial value, initial state, final state. N2 minus N1 divided by, it is not R, R1 is the radius of the curvature of this, equals N2 final value divided by image distance. Image distance is V1, V dash. N2 by V dash minus of initial value. This is initial value divided by the object distance. Object distance is this. So this is the equation for the refraction like this, with these notations. Let us apply the same equation for the refraction at this point. This is the point of refraction. Understand, the initial state is here, light is passing from the initial state to the final state. So this is initial state, this is final state. Initial state value is N2, final state value is N1. And what is the object distance? Is the object distance for this refraction is V dash. Image distance for this refraction is V. And the radius of curvature of the second surface is R2. It is the same technique. That means final value minus initial value. I said final value minus initial. Final value minus initial value. Final value is N1. Initial value is N2. The radius of curvature of the spherical sphere R2 equals final value is N1 divided by the image distance. V is the image distance minus of initial value divided by the object distance V dash. This is what the equation for this refraction. There are two different refractions. When you apply the equation, we get the equations like this. The resultant is a combination of these two refractions. Hence, we have to add up the equations for a resultant value. Addition of the equations. Equation 1 plus equation 2. So, equation 1, left hand side, right hand side, right hand side. Add them up separately. Left hand side of the equation plus left hand side of the equation. Equation 1, equation 2. On the right hand side of this equation plus right hand side of the equation plus. So, this plus this equation in the summation, sum of the two equations. Left hand side, right hand side, add them separately. And in this addition, we get the same terms n2 by v dash, n2 by v1. One is minus, other is plus, get cancelled. Write the remaining, taking out the common factor. Here n2 minus n1 is here n1 minus n2, take out minus common factor, becomes n2 minus n1. n2 minus n1 becomes common factor, that is 1 over plus 1 over r1. Here becomes minus, after taking minus common factor, minus 1 over by r2, that is left hand side of the equation equals n1 is common factor, take out n1 common factor, remaining is 1 by v minus 1 by u. Again rearrangement, taking n1 to right hand side, that is divided by this, and this is one side is, this is side, right side and first or right, 1 by v minus 1 by u, that is equals to n2 by n1 minus n1 by n1, that is 1, and remaining is this. This is one equation we get, and one more equation we can get it by following assumption. When u equals infinity, v equals f. What does it mean? When the object is at infinite distance, image is always forming at the focal point, that is distance of image equals f. When the object at infinite distance, the image either by converging or diverging, it is always at the focal point of the lens. Therefore, v equals f. If so, what would be the equation? So, this equation becomes 1 by u, 1 by v becomes 1 by f, and 1 by u, that is 1 by infinity is 0. The term becomes 0. Remaining is this. The same equation we get it like this when the object is at infinite distance. And one more equation we can get by comparing these two equations, because right hand sides are same, left hand sides must be same. 1 by f equals 1 by v minus 1 by f. To the right hand side of the equation 4, same as right hand side of equation 3. These two get this equation. The differences, these two equations for the object at infinite distance. This is the equation for the object at a finite distance. U means at a finite distance like this. Infinite distance means. So these equations, all these three equations are lens maker's formula. We can use this equation for the calculation of u, that is the position of image supposed to get expected, using these values. What are the possible values of this? Suppose the object is at infinite distance, like viewing the objects in the interstellar long distance. This would be the equation. What would be the image formation of this f value using this equation you can calculate. And this is all related to f and v and u, another one. All these equations are the equations which is used for making of lens, that is desirable characteristics. Each lens in the instrument has its own function, the specific function. It also depends on its position in the instrument and the focal length of the lens. That is possible value. For a possible value of f, what are the values you are supposed to take, R1, R2 and N2. Accordingly, we make the material. It is known as lens maker formula. This